Okay, so thank you very much for the invitation to this workshop. So today I want to present you some recent developments in the area of tropical convexity. So my talk is about an upcoming paper together with Georg Loho, which is about signed tropical convexities, signed tropical half spaces, and separation theorems. Okay, so my plan for this talk is very simple. So first of all, I will tell you about our motivation. Why do we study signed tropical convexities? Then I will define these convexities in a little bit more detail than Georg did in his talk. And finally, I will present to you our main results. So what can we show about these convexities? Okay. So after listening to already a few talks about tropical convexity, I hope that you already know these 4 things about tropical convexity. So the first thing that you hopefully already know is that this tropical semi-ring is a structure with R and minus infinity, in which we replace the addition by the maximum operation and we replace the multiplication by the addition. So the second thing to note is that all tropical numbers in this sense are non-negative. And this is because the neutral element of maximization is minus infinity, and every number is greater than minus infinity, so all numbers here are non-negative. And the third thing to note is that in this tropical semi-ring, we have a good notion of tropical convexity that basically mimics the notion of convexity over the real numbers. So we say that a set is tropically convex if it is closed by taking convex combinations of points, right? And here we don't need to have any positivity condition on the weights because all weights are positive in this sense. Okay. And the last thing to note about this tropical convexity for this presentation is that we have a good notion of a tropical half space. So a tropical half space is simply a solution set of this kind of a two-sided affine inequality, which can be written in this way using the tropical notation, or in this more explicit way using the classical notation. And there are some technical conditions needed for this coefficient so that the solution set is non-degenerate. Okay, so this is this standard notion of a tropical convexity, and this notion already gives us some interesting applications. So, for instance, on the one hand, we have this connection with the theory of mean payoff games, and on the other hand, we have this connection with the classical convexity over the reals, namely, as mentioned in the talk of Stefan, the tropical convexity can be thought of as this kind of a logarithmic limit of convexity over the reals, so that the tropical polyhedra are this limit polyhedra defined over the Piso series. And this allows us to transfer some results about classical polyhedra to tropical polyhedra and the other way around, so that we can speak about tropical simplex methods and its ramifications, or we can speak about tropical central path and then use this tropical central path to show some results about the classical polyhedra. Okay, so this is all very nice. However, one important thing about this tropical convexity is that, as we mentioned, all tropical numbers are non-negative. And what it implies is that this tropical convexity is more closely related to the tropical convexity over the non-negative orthant of the reals rather than the convexity of the whole real space. And this sometimes can be very different. So here is an example. So here I have the tropical plane, right? And I have 3 lines in this tropical plane. And so these are 3 generic lines. They have nothing in common with each other. But as we can see, these 3 lines do not intersect at all, right? Even though 3 generic lines should intersect in 3 points. And this is exactly because these 3 lines mimic what should happen in the non-negative orthant of the plane rather than what should happen in the plane as a whole, right? So one of our motivations is to obtain some notion of tropical convexity that more closely resembles the convexity of the whole real space. And in order to do that, we will extend the notion of tropical numbers in order to obtain signed tropical numbers. So how do we obtain these signed numbers? So this is done in a purely formal way. So you just take two copies of the tropical numbers and you declare that, okay, one copy are the positive numbers, the other copy are the negative numbers, and you denote the negative numbers with this minus sign. And then when you have these signed numbers, you can order them, and this order mimics what happens on the real line. So you have a tropical 0, so this is in the middle, and then tropically positive numbers are greater than tropical 0, and tropically negative numbers are smaller than tropical 0, and the tropically negative numbers are ordered in the opposite way than the tropically positive numbers. And okay, you have the same behavior as of the real line. And you can even formalize it by saying that, okay, now that I have these tropically signed numbers, I have also an absolute value function that simply forgets the tropical sign of a number. So the absolute value of minus 2 here is -2. I just forget this first tropical sign. And in this way, this function that to x associates its sign times the exponent, so this signed exponential function, gives you a homeomorphism between the signed tropical numbers and the real numbers. So we can simply say that this signed tropical numbers is just a fancy transformation of the real numbers using some kind of a signed logarithmic function. Okay, and then if you think about it for a while, then you will figure out that there is basically one canonical and reasonable way to define what is a half space in these signed tropical numbers. So as you can see, the expression is very similar to what we have seen before. And indeed, in the non-negative ortant of the tropical numbers, this is exactly what we have seen before. And so now how this expression extends from these non-negative numbers to signed numbers, well, this is done in the following way. So suppose that you are in the ortant in which the variable x1 is negative. Then what you do is you take the expression that you started with from the non-negative ortant and you simply swap the two terms that involve the variable x1, right? And you do the same for all of the variables. So you just swap the places, right? This term may be sometimes on the left-hand side and sometimes on the right-hand side, depending on the sign of your variable. You do this for all the variables. And this is how you extend the notion of a half space from non-negative tropical numbers to signed tropical numbers. So let me show you how it looks on our example. So here we have exactly the same three lines as before, but now I extended them to this signed tropical plane. And we see that in this signed tropical plane, our three lines intersect in 3 points as they should. But, well, it so happens that these 3 points of intersection simply are not non-negative tropical points, right? But already here we see that the combinatorics is a little bit more close to what happens over the rails. And in the talk of Georg, you have seen that this kind of arrangements of tropical hyperplanes are linked with oriented matroids. While what I want to do in my talk is to discuss if in this context we can make a proper theory of signed tropical convexity. So to define segments, polyhedra, separation, Minkowski-Weil theorem, Fourier-Motzkin elimination, and things like that. Okay. So now we move to the signed tropical convexities, but as in Georg's talk, before I can define you a signed tropical convexity, we need to talk a little bit about the problem of addition of these signed tropical numbers. So as Georg already mentioned, well, this is some kind of an issue because a tropical semiring really is a semiring. So a maximization doesn't have an inverse operation, so we cannot simply take two numbers and subtract them, right? And if you try to do this naively, let's say by saying, okay, if I have 2 and -2 and I try to add them, so maybe they should cancel, so I will say that this is -infinity, then this kind of an operation is not even associative. So this is a very bad operation from the algebraic viewpoint. So you need to do something more clever. And one way of doing something more clever is to define the multi-valued addition of signed tropical numbers. So here is the definition of this addition and so how it behaves. So first of all, if you have the same number, let's say a plus a, then the result is a. And now if you have two numbers that are different in the absolute value, then the number with the higher absolute value is the result. Okay. So, and now basically the only problematic case for this multi-valued addition is exactly this case. So it is when you have the two numbers with the same absolute value, but they differ by a sign. And in this case, the multi-valued addition will tell you that the result of this operation is the whole interval between -2 and 2. So here it is multi-valued only in this case. And now this structure with this addition is quite nice because it is a hyperfield. So it is basically like a field, only that the addition is multi-valued. Okay, and now since we have such a nice structure, you can define a notion of convexity, right? And this was done by in the paper of Loho and V. And they said that we will say that a set is TO-convex if it is closed by taking non-negative convex combinations with respect to this multi-valued addition, right? So we have here such a combination, and now we have to add this condition that the weights are non-negative because we also have the negative sign, negative tropical numbers. And this will be our definition of convexity. And so before continuing, let me mention that this is actually not the first definition of signed tropical convexity that was proposed in the literature. There are some earlier definitions, but I will not have the time to discuss these definitions. Okay, so in order to get some intuition about this definition of convexity, let us look at the segments that appear in this convexity. So the first case is that suppose that I take 2 points on a plane and suppose that I take them at random. So they are a little bit generic with respect to each other. And now we can compute what is the segment between those 2 points using our definition, right? So if you take these points at random, then what you would obtain is that the segment between those 2 points is actually a union of ordinary segments as in this picture. And also what you will observe is that in this case, the addition is multi-valued, but it is multi-valued on at most one coordinate at a time. So for instance, here is one combination of these 2 points such that the addition is multi-valued on the first coordinate, but not on the second. And here is another combination such that the addition is multi-valued on the second coordinate, but not on the first, right? So this first combination gives you this part of the segment. The second combination gives you this part of the segment, and the remaining parts of this segment are the remaining combinations. Okay, so this is what will happen for 2 generic points. However, you can also take 2 non-generic points. So here I modified a little bit the previous example. And in this case, what you will note is that the addition may be multi-valued for some combinations on multiple coordinates at the time. So if I take this combination of these 2 points, you will see that this is our result. So when I do the multi-valued addition on these 2 points, I obtain a whole box, right? And in this case, the TO segment between those 2 points has dimension greater than 1. So this is this TO segment between those 2 points. And now you may say, well, it looks like a bug. It shouldn't be like that. The segment shouldn't have dimension greater than 1. But this is actually not the case. Because if you look at all of the lines between those 2 points, then there are many such lines. So for instance, this is one line between those 2 points. This is another line fragment between those 2 points. And there are actually many, many lines that connect these points in this, that pass through this rectangle. And actually all of these lines will even fill in this rectangle. So it is quite reasonable to say that the convex hull of these 2 points should contain all of these line segments between those 2 points. And so what Loho and V were able to show a bit about this notion of convexity is the following 2 things. So first of all, they showed that every open tropical half space is TO-convex, and then they obtained a separation result saying that if you have a collection of finitely many points, then the TO-convex hull of these finitely many points coincides with the intersection of all open tropical half spaces that contain these points. So this is a type of a separation theorem. So you can say that this notion of TO-convexity works really well with respect to the open tropical half spaces. However, when we are talking about polyhedra, we often talk about closed half spaces rather than open half spaces, right? And it turns out that the case of closed half spaces is much more delicate. Like, for instance, here you have an example of a half space. And yes, so the interior of this half space is TO-convex, as the lemma says. But if you look at the closure, then the closure contains our two problematic points, right? However, this closure does not contain the two-dimensional rectangle between those 2 points. So this closed half space is not TO-convex. And it turns out that this is a typical behavior for closed half spaces. Usually closed half spaces are not TO-convex, so they don't really fall into this framework. So now this is where our work starts. So we are trying to make a notion of convexity that will somehow, correct this situation. Okay, so in order to introduce our notion of convexity, our new notion, I need to introduce our new version of addition, right? So the addition, the type of addition that we use is the left sum that Georg already discussed. So the left sum behaves exactly like the multi-valued sum in all of the non-problematic cases, but in the problematic case, it is non-commutative. So it simply says that in the problematic case, the result is the number on the left. So -2 plus 2 will be -2, while 2 plus -2 will be 2. Okay, so this is a nice operation. I mean, it is non-commutative, but many operations in mathematics are non-commutative, so maybe this is not such a bad property. And there are even more motivations to study this operation, because it turns out that this operation is a kind of a generalization of the operation of composition of signed sets from the theory of oriented matroids. And this is why this kind of an operation was already used in the tropical context, at least in these two works. So now, since I introduced you another addition operation, you may think that, okay, so the other notion of convexity will simply say that a set is convex if it is closed by this kind of a convex combination with respect to this left sum addition, right? And indeed, this is a part of our definition, but this is not the full definition that we propose. And let me explain why this is not the full definition that we propose. So in order to see that, let us go in dimension 1. So suppose that I have these 2 points, -2 and 2 in dimension 1. And suppose that you try to make all of these convex combinations with respect to the left sum. Then what you will discover is that the only thing that you get are these 2 points, -2 and 2, and you don't get any other point, right? However, it is intuitively clear that the segment in dimension 1 between -2 and 2, well, it should be the whole interval between -2 and 2, right? And likewise, if you go 1 dimension higher in the plane, you can take these 2 points, right? So they share the first coordinate, but they differ on the second coordinate by a change of sign. And then again, it is intuitively clear that the segment between them should be this set, 3 times the interval between -2 and 2. And again, you will not obtain this using only this kind of combinations with respect to the left sum. So what is our full definition? Well, our full definition is as follows. We will say that the set is TC-convex if it has the following 2 properties. So first, it has to be closed by taking these combinations with respect to the left sum. But secondly, if you have 2 points in your set that differ only on 1 coordinate, and on this coordinate they differ only by a change of sign, then you want the whole interval between those 2 points to be included in your set. Okay, so this is one definition, and there is also a second definition that Georg mentioned that uses union of faces of hypercubes. I will not present this definition, but I can discuss this later. but this definition is enough for our purposes. Okay, so now in order to get a little bit of intuition about this TC convexity, let us again look at segments. So for two generic points, nothing changes. So for generic points, the CC segment and the TO segment is exactly the same union of ordinary segments. And why is that? Well, this is because, as we already discussed, for two generic points, the addition, the multivalued addition is multivalued only at one coordinate. So you have to jump, let's say, only through one coordinate hyperplane at once. And I gave you the second property of TC convexity that allows you to do that. So the TC segment and TO segment will be exactly the same thing. So what changes is in this non-generic situation. So in the non-generic situation, previously we had this rectangle that was a part of our segment. So now this rectangle will not be a part of our segment. And in fact, only these 2 points will become a part of our segment. So in total, in this example, this is the TC convex hull of this point and this point, right? So as you can see, a TC convex set may be disconnected. And now you may say, okay, so this is really bad. It shouldn't be like that. How can you have a good notion of convexity in which sets are disconnected? So now in the remainder of my time, I will try to convince you that this is really a nice notion of convexity and that you can prove some interesting and non-trivial properties even for such a notion of convexity. Okay, so let me go to our main results. So let me start by some basic results. So the first basic result is that every TO-convex set is TC-convex. So a TC-convexity is a weaker notion than the TO-convexity. So this is just by the definition of these two convexities. Secondly, every closed tropical half space is TC-convex. So the TC-convexity captures not only the open tropical half spaces, but also the closed tropical half spaces, which is already nice. And the third proposition is about the topological properties. So if you have any TC-convex set and you close it, then the closure is also TC-convex. And interestingly, if you have a TC-convex set and you look at its interior, then the interior is already TO-convex. So it is stronger than TC-convex, right? So this is exactly how the half spaces behave, as we have seen, but this is actually true for arbitrary TC-convex sets. So in particular, what this proposition means is that if you have an open set, then it is TC-convex, if and only if it is TO-convex. So we can say that for open sets, there is no ambiguity of definition, right? There is a unique notion of convexity for the open sets. Okay, so these are the basic properties. So for more advanced properties, let me present to you the Carathéodory theorem that we were also able to show. So a Carathéodory theorem should say, well, similarly to the standard theorem, that if you have any kind of a set, then a point belongs to the TC-convex hull of this set, if and only if there exists some finite subset such that this point belongs already to the TC-convex hull of this finite subset of set X, and the cardinality of this finite subset only depends on the dimension. And we are able to show that with this Carathéodory constant of the following form. So CD is equal to 2 to the power D times D plus 1. So this is much higher than for the usual convexity where you have D plus 1. And we are actually able to show that this Carathéodory constant has to be quite high. It has to be at least 2 to the power D, as given by this example. So if you look at the vertices of these hypercube with absolute value 1 and all of the signs, then minus infinity belongs to the TC-convex hull of this collection. However, if you take at least 1 point from this collection, then minus infinity will not belong to the TC-convex hull. So this constant has to be at least 2 to the power D. However, as you can see, there is some gap between those two things. And now this gives us our first open question. Well, we don't know what is exactly the optimal value of this Carathéodory constant. Okay. And so in the last part of my presentation, I want to tell you about our remaining results about separation theorems. So in order to analyze separation theorems in these convexities, we use an approach based on the so-called abstract convexity structures. So I don't have the time to present you the full definition of an abstract convexity structure, but let me just mention that you can define a convexity on a space on which you don't have addition, don't have multiplication, don't have order, don't have topology and things like that. A convexity is a very, very abstract notion. And then you can study separation theorems in this very, very abstract context. However, if you have some very abstract space, then you cannot hope to have a separation by half spaces, because you cannot define a half space without any sort of addition, right? So in this abstract context, what people study is separation by hemispaces, where hemispace is a convex set whose complement is also convex. So for instance, half spaces in RD or TC half spaces in the signed tropical convexity are hemispaces in this context. And we have this theorem, this separation theorem of Czepol, saying that for any interval convexities, the following two properties are equivalent. So the first property is a separation property, saying that if you have two convex and disjoint sets, then there exists a hemispace that separates them. So V1 is on the one side of the hemispace and V2 is on the in the complement of the hemispace. And this separation property is equivalent to a property of only 5 points in your space. So if you have a collection of 5 points that are in this configuration that I showed you here, so D is on the segment AB and E is on the segment AC, then these two dashed line CD and BE should intersect, as we see here in the planar case, right? So what I want to say about this theorem is that, first of all, the proof of this theorem uses the Kuratowski-Zorn lemma. So this is based on the axiom of choice in order to find these hemispaces that separate two convex sets. But on the other hand, this theorem is very nice because you have this abstract separation property, and this abstract separation property is reduced to a property of only 5 points. So if you have only 5 points, then you may hope that it is not so difficult to prove, right? And indeed, we were able to prove that the TO-convexity satisfies this Pasch property of the 5 points. So in particular, it also satisfies the Kakutani property. And we have a separation in the TO-convexity via hemispaces. And then we were able to show that these hemispaces that, which we use in this separation result are actually very, very close to half spaces, in the sense that if you have a TC hemispace that is non-trivial, then it is sandwiched between some closed half space and the interior of this closed half space. So a hemispace is basically a half space that is missing maybe some parts of the boundary. So now if you just combine these theorems, we now obtain a separation result that is an analog of the hyperplane separation theorem in Rn. Namely, if you have two disjoint TO-convex sets, then there exists a closed tropical half space that separates them weakly. Namely, X is included in one part of the closed half space and Y is included in the closure of the complement. And as a corollary, we get the same theorem as in RD. Namely, if you have any closed TO-convex set, then this closed TO-convex set is an intersection of closed tropical half spaces. Okay, so we have this nice separation theorem for the TO-convexity, but it turns out that the case of TC-convexity is more complicated than that. So what we observed is that the TC-convexity, unfortunately, does not satisfy the Kakutani property. So you cannot hope to separate two arbitrary TC-convex sets via a half space. However, we were able to show that the TC-convexity satisfies a somewhat weaker property that is called S3 and is also used in this abstract convexity setting. And after some additional work, we were able to prove at least this kind of a separation theorem, that the TC-convex hull of finitely many points coincides with the intersection of all closed tropical half spaces that contain these points. So this is a counterpart of this theorem on Loho and V about the TO-convexity, in which here you had the TO-convex hull and here you had all open tropical half-spaces. So now we have closed tropical half-spaces. And the proof of this theorem is not only based on this abstract convexity and on the Kuratowski-Zorn lemma and on the characterization of hemispaces, but also at some point we use the Piso series. So this is really quite an involved proof. But nevertheless, when you have this kind of a theorem, then you have already quite nice corollaries. So let me give you one such corollary. So as a corollary, we can get the signed version of the tropical Minkowski-Weil theorem. Namely, if you have a signed tropical set, then the following are equivalent. So X is the TC conic hull of finitely many points, if and only if it is an intersection of finitely many closed linear tropical half-spaces. So to sum up my talk, I will say that the TC-convexity is precisely the convexity that gives you the tropical Minkowski-Weil theorem. And to conclude, let me say that, okay, since this is the first work about the TC-convexity, we obviously have many, many open questions. So for instance, we don't know if we can make the constructive versions of our proofs without the axiom of choice or without the use of Piso series. We don't know if every closed TC-convex set is an intersection of closed half-spaces. We only know this for for hulls of finitely many points. We don't know what is the optimal bound in the Carathéodory theorem. We have not yet developed the Fourier-Motzkin elimination for this TC polyhedra. And like Georg mentioned, there are some questions about oriented matroids arising from generic arrangements of signed tropical hyperplanes. It may also be interesting to study the combinatorics of the signed tropical polyhedra. For instance, what is the analog of the Macmillan bound? And I think that there may also be some interesting application of the signed tropical convexity in other contexts, such as the polynomial optimization, and for instance in the hyperbolic program. Okay, so thank you very much.